So let's look at this warm-up. I picked it because you have a question well, it depends on which version you have, because I'm now creating multiple versions to your test. But there's going to be most likely on every version a question very similar to this one, not exactly, but similar. And I want us to think about how to answer it. So good question came up from Cameron. Cameron, can you say it for everybody to hear? You said, is this with or without replacement? And why does that matter? Because it absolutely does. Why is that important? It changes what? It changes, yeah, it changes the probabilities. What you're thinking about is the denominator, right? It changes the total that you're pulling from. So you're both correct in that essence. So we know that that's a question to ask ourselves. And so I didn't say, so we're going to assume without replacement. Okay, if it's not said that, we assume that. Second question is, what strategy am I using here? So you remember we made a list of strategies and we talked about them, and we want to ask, is this a Venn diagram question? No, because there's no word both. Is this a tree diagram question? No. Is this a formula question? Not really. What is the strategy we're using? Slot diagram. Good. That's probably what we're going to do. How many slots am I drawing? Good. So we'll do 1, 2, and 3. And we are multiplying, so it's sort of a formula question because it's one and the other and the other. And we're going to have some things here. The first card. Okay. What's the probability of getting the first card being an ace? Matt? Right, there are 4 aces out of 52 cards. I agree. Times. How about on the second card? Go ahead. Right, I have 3. If I have one card in my hand that's an ace, I now have 3 left in the deck, and I have 51 cards left in the deck. Perfect. And then how about the third card? 2 out of 50. Perfect. And I am going to multiply all of those together. And you would show me this work, obviously, on a test or a quiz. And what do you get for an answer? I got like something with an E on it, right, on your calculator. Remember we talked about what that E means? If the E has a negative, that's the calculator's way of doing scientific notation. So let's write it without the E because I don't want to see it written as an E, nor does AP. Okay, they don't know what they call that calculator speak, and they don't want to see that. So let's write it as an actual number with a negative exponent, or E to the negative 4. Is it 4 or 5, 4? You're going to move the decimal place 4 places to the left. Is it 4 zeros then? No, 3 zeros, right? 3 zeros, and then it's 2, 3, 4? Double check me. Oh, I'm sorry, 181, really, isn't it? All right, so 181. All right. Will be 099, but that second 9 would round it up, right? Okay. Do we agree with this? Okay. So now my next question, this is the first question. The second question becomes, what is the probability of getting a 3 of a kind? How is this question different? I'm sorry? How is it different from that one? Is it different? Is it the same question? Nope, it's still 3 aces in a row from the first question. What's different? I can be not only 3 aces, or I could have 3 2s, or 3 3s, or 3 4s, or 3 5s, or, do you see what I'm saying? Like I have any 3 of a kind. Okay? So how do I address that? How many of those options do I have, by the way? So I have 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, jack, king, queen, ace, right? So there's 13 different 3 of a kinds. Does that make sense? Okay. So how do I do that here? Well, I'm going to have 13 groups of slots. I can have that being my 2s, that being my 3s, that being my 4s, that being my 5s, and so on. Do you understand what I'm saying here? Isn't this probability that, backwards because I'm upside down now, but I will get over it. Isn't this probability the same for each of these? Right? Because don't I have 4 2s? Don't I have 4 3s, 4 4s, 4 5s, 4 6s, 4 of a kind of any of them, right? So this slot that you see here really applies to anything. But how do I take this probability I found with aces and now apply it to any 3 of a kind? Where does that 13 come in is my question. Exactly, Josh. Okay? I have 13 groups. I could have 3 2s or 3 aces or 3 5s or 3 6s or. So each of these, when I multiply them all together, are going to be this. How many of these 0.000181s do I have? 13 of them. And when I add 13 things together that are the same, isn't that the same as just multiplying by 13? Is it a 3? Okay. Do you understand where that's coming from, where that 13 is coming from? I'm adding it 13 times. So when I multiply this by 13, what do I get? So 0, 0, 2, 3, 5. Okay? So it's 1 less 0, so it's a little bit easier to get a 3 of a kind than it is to get 3 aces, and we kind of expected that. You put this number and you multiplied it by 13? Yeah, that's okay. That's an important. When would it become when I raise it to the 13th power? Because sometimes we do that. When do I multiply by 13 versus raise it to the 13th power? When I'm multiplying them, when I have the slot diagram, right? And I'm multiplying them 13 times. I have 13 cards and I'm replacing that. It's with replacement. The probability is all the same. That's when I raise it to the 13th power. Excellent. That's going to come up later today. Okay? All right. We're going to go ahead and go over our quiz. I'm going to pause the recording and come back to it after we talk about the quiz, but let me hand it. If you look at the practice test, the very first question, how nice of me to give you the Venn diagram. I've told you the strategy to use, right? So what I want you to do is go ahead and complete the Venn diagram and then either use the Venn diagram or use the formulas. And if you use the formulas, that's fine. Just show me how you did that. And we'll go ahead and start with this question. Okay, so work on the question 1 for me first, and then we'll progress through. So when we look at a Venn diagram that looks like this, how many pieces to the Venn diagram do you need to fill in? 4. Okay, so if you have a Venn diagram to fill in on your test, make sure you're filling in all 4. Where do I start? The middle. And honestly, if you read the problem, what is the key word that I needed to use a Venn diagram? Both. And sometimes they can have the word and, because and means both. And the and is what happens here in the middle, correct? It's where the overlap occurs. So it could be the word and, it could be the word both. But we'll look at both. So we're going to start with 0.34 in the middle, which is where we started here. And then we're going to kind of work backwards and do our subtraction to find the other parts. If I have cookies as 0.72, then I'm going to subtract 0.34 from that, and I get 0.38 as cookies only. We'll also subtract 0.34 from the milk of 0.44, and I get 0.1. And then what's the one that's missing? None. Okay, so neither cookies nor milk, and that would be 0.18, because you know that all the numbers inside the Venn diagram have to add to be 1. Now, if we're going to simply only use our Venn diagram to answer these questions, that is perfectly okay. You're just going to show me that's what you did. So in part A, if I'm using only the Venn diagram, which I see most of you use the formula, perfectly okay. But what numbers am I adding together from the Venn diagram to answer question A? How'd you get that? How'd you get 0.72 using the Venn diagram? It's actually 0.82. What am I adding? So tell me the numbers. Uh-huh. Uh-huh. Yeah, I'm adding everything inside the circles. If one or the other is going to happen, it's everything inside the circles. That happens to be 0.82. Okay? Now, there is another way. There's actually two other ways to do it. Could I have also just said 1 minus 0.18 and use the complement? That's okay. Most of you, as I walked around and was looking, used the formula. Perfectly okay. But if you use the formula, you have to show me context. Cameron. Right, or one or the other. It doesn't say only cookies or only milk. It just says one or the other. It could be both. So let me use the formula. Okay, let's use the formula. You ready? The formula says, I'm going to come down here so I have some room. Probability of milk or cookies. Okay, cookies or milk, same thing. It is the probability of milk plus the probability of cookies minus the probability of milk and cookies. Cookies and milk, same thing. Agreed? That's the formula. As I walked around, if you use the formulas, a lot of you guys did not put it in context. If you're using a formula, you better put it in context. So let's see what it is. Probabilities of milk. Again, I'm not using my Venn diagram here. I'm just saying all of milk is 0.44. All of cookies is 0.72. And then cookies, both cookies and milk is 0.34. Those also add to be combined to be 0.82. Either way works. Either way works. The reason I can add everything in the side of the Venn diagram, I've already done my subtraction in there, right? I've already taken care of the subtraction inside the Venn diagram. So that's why I have to subtract in my formula. Okay? Same thing. It's just different strategies. Okay? Now, for part B, doesn't the Venn diagram just clearly just answer that? We're looking at only cookies. What number is that? 0.38. Yeah, exactly. All right. And then, hallelujah. Okay? C, I'm explicitly told given that, which means I know for a fact I'm going to use conditional probability. Okay? So this is key. They don't always have that, but when they do, I definitely know. So I know that I'm going to write it in context. I have cookies given milk is probability of cookies and milk divided by the probability of milk. Don't forget, you divide by what follows the given that. Cookies and milk is what number? 0.34. And probability of milk, no. Probability of milk is all of milk. 0.44. Okay? Which happens to be 0.0773. Red and green. Okay? Okay, so far. I think it's important to go through one of these problems very explicitly so you know what you're using the Venn diagram for, what you're adding, what you're not adding, and what you're putting in the formulas. Formulas and context, essential. All right, next question. Well, gosh, Miss Macker, you're telling us everything. I actually said draw a tree. Guess what I'm not going to do on the test? Tell you to do that, okay? So just make sure that you can read this problem and maybe you can ask yourself, why is a tree necessary here? Okay? And I'm going to give you a few minutes to actually draw it. So go ahead and work on that. What tells us in the problem it's a tree diagram? How do I know? There's multiple outcomes. There's more than one thing happening. We have some disease issues, and then we have the test issues, right? So be able to detect it, whether they have a positive or negative outcome on the test. So we have two different outcomes. Actually, there's 4 different outcomes, but 2 different variables, whether they have the disease or not, and whether they test positive or not. Another way to think about this is could I put it in a contingency table? Are there multiple variables? I could. I have yes or no on the disease and positive or negative on the test. So there are 2 distinct variables here. But a tree diagram is what I would suggest. So complete your entire tree diagram. Do the multiplication. All right, so what are, sometimes the tree starts with 2, sometimes it starts with 3. I think it starts with 2. What's my first variable here? Disease or no disease? And I'm just going to use a squiggle. You can use disease complement, the little C up there. That's perfectly okay. And we're going to go ahead and add some information. You want to finish that? Okay, James. Oh, thanks. All right. So we're going to want to add the probabilities here. So what numbers go where? Reading the problem, I have what goes where? I love that you can convert percents properly. So 2% of the disease definitely has the disease. And we know that any branches have to add to 1. So what percent don't have the disease? 0.98. Perfect. All right. Then we're going to continue, and it does say that for those people who have the disease, so I know I'm up at the top branch of my tree, it says the test is able to correctly detect it, which means that they have the disease, they got a positive on the test. Would you agree? Correctly detect it 99% of the time, which means it comes out as a negative what percent? 0.01. Okay, good. We'll keep reading, and it says, however, the test gives false positives. So false positives means that I actually get a positive when I don't have the disease. That's what a false positive means. 5% of the time, which means that it correctly diagnoses you as not having the disease, what percent? 0.95% of the time. I'm sorry, 0.95% of the time. I'm going to continue my entire tree now because I am going to find all of the probabilities, the disease and positive, disease and negative, no disease and positive, and then no disease and negative. And I'm going to multiply through my tree and just double check my math here. But this is what I got. Let me know if you got this as well. Yeah. I didn't know. You're going to show me the context. Okay? So I know what you're multiplying. Okay? What should all the numbers in blue add up to be? 1. So if they didn't, you knew something was awry, right? You knew something was up. And some of you on your quiz, if you had done the tree and added them up, would have seen that you would have gotten them add to be more than 1, which would have been an issue. So always check that. Okay, that's a kind of a it's to help you really more than anything, to make sure that you've got the numbers correct. All right, so I've got my tree done. So now some of the questions start appearing. Okay, the first question says, what percent of the population will test positive for the disease? So when I look back at my tree, what am I looking for here? What 2 numbers? Well, I just told you the hint. What 2 numbers? They're going to test positive, really. They're going to test positive and have the disease, or they're going to test positive without the disease, right? So those you're going to add together. It's one or the other. So that means that I am looking at adding 0.0198 to 0.049. I'm showing my work here. Not in this particular one, because the tree is your context here, because those are numbers I found, they directly come from my tree, so it's okay. All right? Any questions so far? All right. Let's look at B. I'm popular today. This is exciting. And the lucky winner is Miss Kennedy. All right. Given that, oh, I love when they say that, don't you? Because that guarantees me to know that I'm going to be doing something specific. Given that, so I know it's a conditional right off the bat. So what's the order of my conditional? What do you think, Maddie? Look at B. Tell me the order that I write it, because I am going to write it in context now. So where does the negative go? Does it go before the slash or after the slash? Actually, it's after. Anything that follows the words given that tells you it goes here. Okay? So that's something to remember. Well, I am right now. So what is the probability that they have the disease? So that's the order of the conditional. And it does matter. Because if you write it backwards, you're going to get a different answer. Okay? So the order of the conditional is very important. So at this point, I'm going to have some work to do. So I'm just going to draw it down here if that's okay, so I have some room. So the probability of disease given negative, let's continue to write the formula in context, because we're going to use the formula. So what do I write for my numerator? Disease and negative divided by the probability of negative. Yay. Good. So at this point, I've written what I need to. I'm just going to put the numbers in. Disease and negative. When I go back here, disease and negative is this number here. Don't you agree? We found it. It's on my tree. 0.0002. That's my numerator. What about the denominator, though? I don't have just plain old negative up here, but aren't the two circled in red the two ways that you can come out negative? So what do I do with those two numbers? Add them together. Very good. So you're going to say 0.002 plus 0.931. And when I divide those, go ahead and do the calculation on your calculator. Because again, something weird is going to happen on your calculator. What do you get? That E thing again. Again, just scientific notation. Please don't ever write it in that notation on the test. But you can go ahead and do the moving of your decimal point, and you should get something along those lines. Did you get that, Boris? You have to, okay, so you have to put your denominator in parentheses. Because the calculator does the order of operations automatically. And I'm actually really glad that that happened. So what you want to do is either put the whole denominator in its own set of parentheses. Okay? Right hand 3. It should be times 10 to the negative 4. Move that decimal place 4 times. Yeah. Good? All right, let's look at C. Go ahead and just look at C here. What % of the population will test positive and have the disease? So it's just, we want this. The probability of positive and have the disease. Didn't we already find that? Positive and disease. Well, that's the same thing as disease and positive. The order doesn't matter, so it's just 0.0198. Okay. Any questions? Pause. Yes, ma'am. Oh, yeah. If it said %, we probably should convert them. I'm not going to be super picky about it, but you're probably right. So let's do that. So 6.88%, okay, since that's what it asked for. And the same thing for C, right? That would be 1.98%. Thank you, Sandra. Exactly right. Yes, ma'am. No, we just said positive and disease. There's nothing more to it than just that. Jenna. And means you multiply. So as we already did the multiplication in my tree. So that's where the 0.02 came for. Then the probability of plain old negative is both of these. Because it's disease and negative or not disease and negative. Okay, so that's where you get it. So you almost always add in the denominator in a conditional probability.
And the second from problem B, the D frequencies of that would have been 0.088.
Yeah, that's fine. That's what I did. Okay? Sure. All right. I need to get to number 3 because it has been a while since we've talked about number 3. And these are not on our formula sheet, so just ignore that sentence. Okay? So what's important is we know how to do it because we've done it, but it's been a while. So let's go ahead and we just write the problem down here. It says to find the expected value, okay, the variance, and the standard deviation. Say, what? Miss Mackert, what are you talking about? Well, we did this back in chapter 3. So that's why we're reviewing, okay? Because it's been a while. So let's talk about it. So in this particular question, I have given you a probability distribution, okay? And we're actually going to, in question 4, come up with it on our own. But in this particular question, again, this is number 3. What should all the probabilities add up to be? 1. So if one's missing in there, you know what to fill it in with, right? Right? Okay. So what in the heck do you think they mean by expected value? What's another word that we've used before that means the same thing? Average, mean. Okay, they mean the same thing, okay? So anytime you see the expected value, that means you're going to be finding the average. How did we do that with this before? By the way, here's the notation for expected value. Here's the notation for mean. They mean the same thing. How did I find it? I add some things together, but I have to multiply some things too. Didn't I take 200 and multiplied it times 0.14, and then I added that to 260, and I multiplied it times 0.18, and I added that to? Do you remember this? We've done it. It's been since September. It's been a while, but it's a review. And then 320, we can use a calculator. We're going to use a calculator in a minute, but I'm showing you the long way first. Okay, 320 times 0.23 plus 400 times 0.27 plus, and then we have 650 times 0.18. And that is the mean. Okay, that is the average. But we also did this on the calculator, if you remember, kind of like the shortcut. So let's pull up our calculator, and let's remind ourselves what we did. Do you remember? List. So we're going to stat edit. So let's do that. So stat edit. And mine happen to be clear, but if yours aren't, they should be. What do I put where? Probabilities in the second list. Sure. So let's do that. So we have 200, 260, 320, 400. Oops, not 40. 400 and 650. And then in list 2, I'm going to put the probabilities of each of those occurring. So let me do that. So I can see each of them. All right. And then tell me where I went. Do you remember? Stat calc. Now don't do this really fast. I don't do 2 variable statistics because that's going to give me 2 different means. That's not what I'm looking for. I just want 1 mean. I do 1 var stats, but my operating system is older than yours. So I need everybody to, on their own calculator, do it because what you see on my calculator will look different. When I went to 1 var stats, I didn't get a menu. You do. It says here, list, frequency list, and calculate. You should see that on your calculator. So stat, calc, 1 var stats. Okay? So list should be list 1. So I'm going to tell my calculator list 1, maybe. There we go. Frequency list is the same place we put our probabilities. The probabilities is the frequency of it happening. So we put that in list 2. So my OS is a little bit different than your OS. Oh, I'm good. What? Let's go again. List 1. This is driving me crazy. List 1, comma, list 2. You should have gotten 373.4, agreed? Here's what I'm going to do. I'm going to take off if you write that.
Wait, what?
See? What? Huh? Who? What? Why am I taking off if you write 373.4? What's the context of my problem? What are my units? Dollars. So what am I asking you to round to? The nearest cent. So context, okay? Just put the units, that's all. If it's dollars, round to the nearest cent. If it's, what's the expected number of cats, write the word cats. If it's the expected number of toes, I don't know, whatever it's asking, put it in context. I gave y'all a visual, right? Gross. Get it. All right. Now, when we did this kind of problem before, and we did standard deviation and variance, we did it by hand. And I made you a promise. I said, I'll never ask you to do it by hand again. Promise still holds true. So let's look at the calculator output. What's the standard deviation? Normally, we use the SX, but I don't have an option for that here. So what should I use instead? The little sigma, the O with the tail, the donut that's got a side ponytail. Okay, so 145.40, round to the nearest cent. Very good. So my standard deviation is 145.40. In context, what's the variance? What's the relationship between the standard deviation and the variance? You square it. So I'm going to take 145.4, and I'm going to square it. That's the variance. The variance is 21,141.16. Okay? So it is stuff we've done before. It's just been a while. So it's probably good to review it if you needed to, right? Making sure we can. Now, question 4 is a little bit more difficult. So I want you to read question 4 and tell me why it's more difficult than this one. I took this and squared it, the standard deviation and squared it. Just squared 145.4. Okay? Why is it harder? Why is the next one harder? Question 4. Miss Macker, are you a cat lady? No. Not any cats. I'm allergic to cats. Highly, actually. I get allergy shots for cats because I can't be in the same room. I get asthma attacks and my eyes swell shut. I'm really allergic to cats. Me and my daughter both. But I have 2 dogs, 2 fish. Used to have a bird. Used to have a lizard. Used to have a, I'm trying to think, turtles. Like we've had turtles. No, it's not me. It's the children. I had to feed the lizard alive crickets. That was not Miss Mackert's forte. The lizard didn't quite get enough light. I like all creatures. I'm not trying to be mean. The lizard? My son was like 4. I don't remember. It was not on purpose. Exactly. Okay. Are we ready? Okay. Why is this one harder? Not because of cats, but because the chart's not there. Oh, Esmeralda, where's my chart? Okay. So The probability distribution was not provided for us. So we need to come up with it. And once the probability distribution's there, I mean, if the chart's there, we can do the calculations aren't hard, right? That's not the hard part. Agreed? Please. So let's decide what the outcomes are. So when we read this problem, it says a cat has 3 kittens. All right. What is the probability distribution for the number of male kittens in the litter? So if we have 3 kittens, don't you agree that all 3 could be male? Okay. What are some other possible outcomes? 2 of the 3 could be male. 1 of the 3 could be male. Or none of them could be male. You know what? Why don't we come up with a sample space? Remember that word? What does sample space mean? All the possible outcomes. So remember, we're looking at males now, right? So we could have, let's start with a 0. No males, which would look like what? Female, female, female. Would you agree? No males. 0 males. What are the outcomes for 1 male? So I could have the male at the end. I could have that little male in the middle. Or it could be in the beginning. Would you agree? Okay. Well, continuing with my sample space idea, what are the outcomes for 2 males? I could have male, male, female. Male, female, male. Or female, male, male. Is my sample space complete? Why? I could have all males, so all 3, right? All right, so I've created my sample space. I've listed all the possible outcomes. This is going to help me, okay? Because I know some things. Based on my sample space, I'm going to fill in the probabilities. The probability of having 0 males means I'm up at the top, okay? So this probability is going to be found here. How do I come up with that? It's a slot diagram inside. We're going to have 0.6 times 0.6 times 0.6. Because I have female and female and female. Are we okay with where the 0.6 came from? Just the complement of 0.4, right? So we're going to have 0.6 times 0.6 times 0.6. What is that? You got calculators? I'm not a human calculator. I just have the answers. 0.216. Using that same strategy, don't you think coming up with 3 males is pretty easy also? What's that going to be? What am I going to multiply to get that? 0.4 times 0.4. Same thing. We're doing male times male times male. In other words, I'm using down here, they're all male, and I get 0.064. The ones in the middle are a little harder. Dun, dun, dun. Why? How many slots am I going to have to do for 1 male? For this to find this probability. I'm going to have to do 0.6 times 0.6 times 0.4, or that, or that. I've got 3 of them to do, don't I?
And 1 equals 1 minus 1.
That's at least 1, not exactly 1. This is actually what's called a binomial situation. You probably have no idea what that means unless you took Algebra 2 Trig, okay, where you had a binomial expansion. This is a binomial situation. We will talk about what it means after winter break, okay? So don't worry about that right now. There is an easier way to do it, I assure you, and we'll get to that. But for now, we're going to use the slot diagram. So I'm going to do one of them, and then I'm going to give you we'll figure out the other answer. So right here, we're going to do some work. Let's use a different color so we don't get confused. So we're going to have female, female, male, or female, male, female, or, so we're going to do female, male, I'm sorry. I wish I could just touch it and erase it. It'd be so nice. Female, female, male. I'm just writing my options here. I'm going to put in the respective probabilities. So 0.6 times 0.6 times 0.4, or 0.6 times 0.4 times 0.6, or, you with me? Yes, ma'am. Yeah. Lexi, you can. Yep. You're going to take these and multiply them, add them to these and multiply them, add them in those and multiply them. I'm going to have you do that. I think it's worth the exercise. So I want you to be pushing numbers on your calculator, Miss Marshall. Several of you figured out that this is the same thing 3 times, right? So if you found 1, multiply it by 3. Perfect. But the answer is 0.432. Now, why don't I have to go through that same tedious process to get the probability of 2 cats? It's not the same, believe it or not. All the probabilities in the distribution should add up to be 1. So if I have 3 of the 4, can't I just subtract it from 1 to find the missing one? So that's a way to do it if I wanted to. But you can just also trust me, and the answer is 0.288. What is the expected number of male kittens? What am I going to do to answer that question? Find the mean. Okay? I've got the probability distribution now. Now it's a matter of just multiplying to find them. Okay? And what had you better put? Or what are we going to round to? Well, it's not dollars. I'm not rounding to cents. I want the number of cats. Actually, I don't want you to round to the nearest cat. Believe it or not. Okay? I know that sounds weird, but you're not going to round this to a whole number. An average still can be a decimal, and it should be. I got 1.2 cats, which you should get. Okay? So the expected number of cats is 1.2 cats. Maybe it has an ear, it's missing a couple of part body, I don't know. All right. So we have about 10 minutes left. I am going to ask that you finish this for homework. Okay, there's not a whole lot left. Shh, guys, excuse me. Shh. There's not a whole lot left to do. But the rest of it is not review stuff. It's review for your test, but it's not stuff that we did a couple months ago. The rest of it's using our strategies, tree diagrams, Venn diagrams, formulas, and etc. Of the papers I handed back to you, are there any that you got questions you got wrong that you weren't sure about? I'm going to pause the recording at this point and go ahead and finish it. But if there are things you'd like to go over, let me know.